Hello, class. I thought I'd set up for another lecture. Yes, I did have a cup of tea. In fact, I still have, or actually it's coffee. I still have the extra coffee right here, just relaxing. Had a plate of brownies in the refrigerator, which I've talked myself into having one. And now what I want to do is I want to come back to sort of where we left off in lecture number 7 and start up there and explain why a joule is a volt coulomb. And you might say coulomb, so voltage times charge equals energy. I better write out energy so you don't think it's electric field or something. V times Q, because let's see if that's true. You know, VQ equals energy. Well, we know what energy equals. We know that energy is a kilogram meter squared over seconds squared, because isn't energy just force times distance, right? And then if we look at that and we look at voltage, we know that voltage is a kilogram meter squared over seconds cubed amp. And we know the charge is an amp second. That's what the combination of primary units are that define a coulomb. So that amp there is going to cancel out with that amp, and that second is going to cancel out with one of those, making that squared. So yep, kilogram meters squared over seconds squared. That's right, it is. That is energy. So voltage times charge equals energy. So the definition of an electron volt is 1 electron volt equals 1 volt, right, times the charge on an electron, which is 1.602 times 10 to the minus 19 coulombs. And I'm using the minus 19 because it's a scientific constant. And so what that gives us is 1.602 times 10 to the minus 19 joules. That's right. So an electron volt is not a unit of voltage at all. An electron volt is a unit of energy, just so that you understand that. And I want to talk about a couple things, dealing with that and an electron volt and what type of, things do we have? What do we talk about in terms of electron volts? Well, obviously an electron has about 1 electron volt, right? If I wanted to fission U-235, so if I was doing a fission, right, which is what is occurring in our nuclear plants and what occurred with the atomic bomb, if I'm doing a fission of U-235, to do that, that requires 270 million electron volts, right? So you can turn that into joules. That's just for one fission of uranium-235, and it's 210 million electron volts for the fission of plutonium-239. Now, if we think about the molecule, right, in the atmosphere, if I was just thinking of a molecule in the atmosphere, that's about 1/40th of an electron volt, right? The kinetic energy of a molecule that we find just floating around in the atmosphere, And how do I know that? Well, I know that using Boltzmann's constant. First of all, what would be the energy that I need to overcome an electron volt, right? And by energy, I mean, what would be the temperature that I would need? And that's where Boltzmann's constant comes in. Well, I'm not going to put the whole thing. It's Boltzmann's constant anyway. And it's 1.38 times 10 to the minus 23 joules per degree Kelvin, or kelvins if you want to call them by their technically correct name, right? That's Boltzmann's constant. And so if I think about Boltzmann's constant, let's look at Boltzmann's constant for 1 electron volt. 1 electron volt. And what the temperature equivalency would be for 1 electron volt with Boltzmann's constant. Well, that would be 1.602, I'm putting it in joules, times 10 to the minus 19 joules, right? And divided by 1.38 times 10 to the minus 23 joules per degree Kelvin. And I think you can see the joules are going to cancel out with one another, right? And the Kelvin, which is in the denominator of the denominator, is going to come into the numerator, right? So that gives us 11,604 degrees Kelvin. And if you remember correctly, the offset for the Kelvin degrees is so 0 degrees Celsius equals 273 degrees Kelvin, or I should say 273.15 degrees Kelvin is it. So you can see this is still like the surface of the sun. So that's the temperature we need to overcome 1 electron volt. Now, what if I needed plasma fusion, right, to actually make a spheromac or a tokamak that could actually give us fusion energy, like they're trying to do at MIT and some other places, trying to make a tokamak, or actually now it's a spheromac in most cases. But I think they've gone back to the tokamak design now again. Anyway, what you need there for the dissociation, or I should say the fusion of that plasma, is 15 kilo electron volts. 15 kilo electron volts. Well, let's see what we've got there. 15 kilo electron volts, as far as temperature goes, is going to be 15,000, right? Times 1.602 times 10 to the minus 19 joules, divided by Boltzmann's constant of 1.38 times 10 to the minus 23 joules per degree Kelvin. And that ends up giving you 174 million degrees Kelvin. And so when we start to put the fusion reactor together, right, that is going to give your children and grandchildren unlimited power for the rest of eternity, we're going to have to overcome this somehow. And hasn't that been the real problem for almost 40 years now? How do you get a bottle that can hold a $174 million item? Right? Where do you get that bottle? It has to be magnetic. I just want to, write a couple things up here. We've got Boltzmann's constant up here. I like to write epsilon sub 0 equals 8.85 times 10 to the minus 12 farads per meter. I'm going to write mu sub 0. Remember, these are only sub 0. Remember the definition of mu and epsilon from the last lecture. 4 pi times 10 to the minus 7 henries per meter, right? So we've got those. We know what the coulombic force is. The coulombic force is just going to be Q1 times Q2 divided by 4 pi epsilon, and that's epsilon of the dielectric or the material, you know, between the individual charges themselves times r squared, right? And then we also know that our electric field equation, if we're just looking at the electric field that's around one point charge, let's say like an electron or a proton, that is just going to be the charge on that particle divided by 4 pi epsilon r squared. And the units for this are newtons per coulomb, or we know newtons per coulomb are also the same as volts per meter, don't we, from the last lecture? So we have all of those equations, and I just thought that I would, you know, put those up there. And, you know, we've discussed several different things here. You know, when we use Boltzmann's constant, let's just think about that for a second. If this is a one-to-one relationship, right, 11,604 degrees Kelvin, how do we know that the kinetic energy of atoms in the the kinetic energy of molecules in the atmosphere is that? Let's think about this. So if we've got that divided by Boltzmann's constant, we know that the temperature of the atoms in the atmosphere are about 293 degrees Kelvin, right? And if I multiplied that by 1.38 Boltzmann's constant times 10 to the minus 23 joules per degree Kelvin, wouldn't the degree Kelvins then cancel out? And that would actually tell me how many joules I had there. Let's just check that out. So 200, if I have a gas at 293 degrees Kelvin, and I've got Boltzmann's constant right there, 1.38 times 10 to the minus 23. That gives me 4.04, I'll say 3 times 10 to the minus 21, doesn't it? And then when I divide that by 1.602 times 10 to the minus 19, oh, wait a second. Sorry about that. 4.043 times 10 to the minus 21 divided by 1.602 times 10 to the minus 19, that gives me about 40. And of course, that's what it is. So this is about 1/40th, right? Equals 1/40th, actually 1/39th of 1 electron volt. So there you go. Oh, I forgot the joules there. So there you go. We can look at Boltzmann's constant to see how much energy. There's two constants that I want you to get out of this equation, though. Boltzmann's constant, and see how to use Boltzmann's constant, and also in this to understand what an electron volt is. That electron volt is a unit of energy. It's not a unit of voltage. Why do we use electron volts instead of using joules? Because at the elementary particle level, it's so much easier to talk about the decay energies of certain particles, like a uranium-235 atom, in terms of electron volts, which is a very small number, as you can see, times 10 to the minus 19. Instead of talking about this, even when I multiply this by 270 million this is still a very small number, right? 270 million, isn't that about, 3 times 10 to the 8? Well, that's 10 to the minus 19. So that's only taking care of 8 of those. That's still usually 10 to the minus 11, which is literally at the pico level, right? So that's why we use electron volts to talk about decays and interactions at the elementary particle level. And I wanted, since you're going to be working with engineers your whole life, you should know what an electron volt is, because you're going to come across it in the literature, throughout your life. Okay, I also wanted to talk about, well, we're going to talk about Planck's constant in just a second, but what I thought I'd do is I would just cut a piece of paper out here and put an equation, E equals mc squared, right? That's an equation, later on, if you ever go into astrophysics or you take, quantum mechanics or whatever, you'll get into the derivation of E equals mc squared. And it's a very interesting, great derivation. I wish I could do it here, but it's really graduate level course. This isn't what we're doing. But what I want to point out is if I could turn 1 kilogram, if I could turn 1 kilogram of material into pure energy, right? How much energy would that give me? I think everybody can see 1 kilogram times c squared. That's going to give me 90 times 10 to the 15 joules. 90 times 10 to the 15 joules. You're probably saying, wow, that's a lot. I guess. I don't know. What is 90 times 10 to the 15 joules? I'll tell you how much it is. On the Earth nowadays, we use 1,500 times 10 to the 15 joules per day. So if I could turn 1 kilogram, right, 90, 1,500 divided by 90, that gives me 16, doesn't it? Right? So if I divide that by 90 times 10 to the 15 joules per 1 kilogram of mass, that means I get 16 kilograms of mass is being changed into, with our energy use on the Earth today, 16 kilograms of mass. If I went through and I sifted through all of the coal ash and weighed it all up and then put it against the actual coal itself and the water vapor that was inside it or whatever, and 16 kilograms of it would be gone, because we've used that and turned that into energy. We've turned 16 kilograms into energy per day on the Earth. Of course, the sun is doing that in a nanosecond, less than a nanosecond, I'm sure. So I haven't actually worked it out, but I'm sure I could. So isn't that great? I just wanted to point that out for you, that E equals mc squared. That really tells us, and of course that also gives you an idea of how much energy we're using in the world in one day. All right, I wanted to talk a little about Planck's constant as well. And in fact, I know it doesn't come up in your first chapter, but I would like to give you an equation that you will see again. And in fact, I saw it straight up, first chapter in most of the, the electromagnetic things that I saw. Energy equals Planck's constant times frequency, right? Planck's constant times frequency of an electromagnetic wave, that gives us the energy in the electromagnetic wave. Pick an electromagnetic wave. Let's say I want 100 megahertz on your FM dial. 100 megahertz wave. So I've got 100 megahertz times Planck's constant, which is 6.626 times 10 to the minus 20 or 34 joule seconds. You know, a lot of times people get Boltzmann and Planck's constant mixed up, but of course, how can you? Uh, I say that because I think I did, and I couldn't remember which was which a long time ago. But yeah, this gives me the energy of a photon. Now let's just remember that it gives me an energy of a photon at that. Now you're saying 100 megahertz. I can't see 100 megahertz. No, you can't. But that is a radio frequency electromagnetic wave, right? Now I'm going to talk about two different things here. First, a radio wave and how much energy is inside a radio wave. Now I think everybody knows 100 megahertz, that's really 1 times 10 to the 8, right? So the energy in that photon, that radio photon, I shouldn't have put that line there. I should have done it anyway. The energy in that radio photon is going to be 6.626 times 10 to the minus 26 joules per photon. I'll put photon down here again so you know that this is with this, right? So 6.626 times 10 to the minus 26 joules per photon. Now the next thing I want to look at is did not even put that on there. I have no idea how long I've been recording, but I think I'm still fine. So let's look at something that's a higher thing. Now, if you remember, I said that frequency times wavelength equals the velocity of propagation. And the velocity of propagation is c over the square root of the relative permittivity. But what if it's air? What if it's traveling in air? Let's say that this photon here is traveling through the atmosphere of the Earth, right? Well, the atmosphere of the Earth, the relative permittivity is 1, basically, 1.0004 or something, but it's basically 1. So the relative permittivity of the atmosphere is 1, and the relative permeability of the atmosphere also is 1. So we really can say that this is traveling at the speed of light, isn't it? So if that's traveling at the speed of light, I'll just put that here for this particular case, traveling through air, right, is going to be at the speed of light. Or I could put, I'll do this. I'll put air for your notes, and then I'll put, you know, c divided by the square root of 1, and that's going to equal c. Now we know that is traveling. So if I had, right, let's go a little further. Let's say that I had a wavelength of 500 or 390. We go into the UV range. 390 nanometers. That's a powerful UV wave, light wave, right? So now, what would the frequency of that be? Now we know the frequency of this radio wave is 100 megahertz because we know FM radio, and we say, oh, FM radio, 100 megahertz, 94.5 megahertz, 91.9 megahertz. It's all megahertz. And every radio channel, by the way, is 200 megahertz wide. I may talk about that too. I'll put a little note here. I may talk about the radios and stuff later. Hopefully I can get a better timer system than I've got here. But I think it's been about a half hour maybe. Maybe 20 minutes. Anyway, so we can easily figure out what the frequency of that is in air. So the frequency in air, right? And I'm saying in air because the frequency through glass is not going to be that, is it? Because the relative permittivity of glass is not 1. The relative permittivity of glass is 1.5, isn't it? So we're just talking about a wave traveling through the air, whether it's a radio wave traveling through the air to your radio in your car, or whether it's a photon like this, right? This is a UV photon. It's traveling through the air to give you skin cancer. So the frequency in the air for this is going to be the speed of light divided by the wavelength. Well, that would be 300 times 10 to the 6 meters per second divided by my wavelength, which is 390 times 10 to the minus 9 meters per second, meters. What? I was looking at 3 different things there, and I heard an email that came in at the same time. So let's figure out what that frequency is going to be, and I think everybody can see that it's going to be a pretty large frequency, isn't it? Because I've got 6 in the numerator and I've got minus 9 in the denominator, and that ends up giving me 76.9 times 10 to the minus 5, or oh, that 0.6. Oh, I'm sorry. Where is my, I can never find it. Anyway, no, I'm sorry, I did that backwards. It is 769.2 times 10 to the 12 hertz. And of course, we know 10 to the 12 is tera. So I could say that it's 769.2 terahertz, right? That's high. That's pretty high. You know, we look and we see that this is our energy for this radio wave photon, right? But let's look at the energy for this. The energy for that then, 769 terahertz times Planck's constant of 6.626 times 10 to the minus 34 is going to give me 509 times 10 to the minus 21 joules per photon. Okay, does everyone see that? And now you can see the difference between those two photons. Look at how much more energy this photon has than that photon. I mean, it has almost a lot more. A million more, right? So a million more, well, million times as much energy. So this has a million times as much energy as that. All visible light and infrared light and UV light, all is much, much higher as far as photons go than a radio wave. And I want you to understand that too. Now, I also want to say, well, what about if this is going through glass? If, you know, the index of refraction for glass is 1.5. So the velocity of propagation through glass, and this is just a review of your high school physics, is just the speed of light divided by the index of refraction. So the speed of light in glass is going to be 200 times 10 to the 6 meters per second, isn't it? That's right. And you know, that has to equal frequency times wavelength, doesn't it? Well, if in air, frequency times wavelength equals the speed of light, and now the speed of light is going 2/3 the speed that it goes in air, and I've still got frequency times the wavelength. Well, if I multiply this frequency times this wavelength, let me just cross those so that you can see them in your notes. If I multiply that frequency times that wavelength, I'll tell you right now, I'm going to get 300 million, not 200 million. So what changes? Does the frequency change and the wavelength change? Does just the wavelength change? Does just the frequency change? What changes? Because it can't be 769.2 terahertz times 390 nanometers anymore, can it? Because that would give me 300 million. And I only have 200 million meters per second now. Frequency never changes. That rule of physics has saved us so many times. Frequency never changes. Frequency never changes. And I guarantee you, I'm going to give you something like this, aren't I? I'm going to give you something like this. I want to show you another thing. Here's what happens when it reaches that barrier, right? Because if the frequency is staying the same, well, then this better get smaller, right? If this stays the same and it's only got 200, it better get smaller. So that's what we've got. We've got a waveform that comes in like this, and I'm going to over-exaggerate it, but here's what happens. The wavelength keeps the same frequency, but the actual wavelength gets smaller. So this is glass, and this is air. Oh, wait. Oh, okay. Air. I was trying to. Glass. Okay. That's it for this lecture, and I'm going to go on with the next lecture sometime. I don't know. I'm going to take a break. I did 2 lectures. Now I get to ride the motorcycle. Okay. See you later.